In some 40 years, it's transformed the French landscape. Its three-letter name becoming iconic in France, TGV. Traversing the country on nearly 3,000 kilometers of rails, the TGV has transported more than 3 billion travelers since it launched in 1981. During that time, it has constantly evolved with groundbreaking technology forever changing the future of train travel. Here comes the TGV-M.
For the TGV-M, we wanted to improve upon everything that made the TGVs a success.
What changes should we make to create something modern that reflects society today?
They came up with an ambitious list.
We chose 400 innovative ideas for the TGV-M.
It's a jewel of technology.
One impressive innovation is called a graft, which can reduce the train's dependence on the national power grid.
It's the only one like it in the world.
This improvement gives the TGV more reliability.
If an overhead line breaks, for example, the TGV-M can travel for tens of kilometers before it stops.
The TGV-M's standout feature isn't its speed. Nowadays, it breaks records for its low energy consumption, a whopping 20% less than the previous generation of trains.
20% is a lot. It's really groundbreaking.
How does it do it? Partly because of its optimized aerodynamic profile.
The shape of the nose is completely different.
You can barely tell the difference between the locomotive and the cars.
While the silhouette has been transformed, the interior has had a makeover too.
This train will be quieter and have more natural light because there are 25% more windows.
Along with its new ergonomic seats, improved internet connection, and two-story bar car, the TGV-M will be able to carry more passengers.
Multiple trains hooked up to one another could carry up to 1,500 passengers at a time.
Not only can they carry more passengers, they're also more adaptable, unlike the old TGVs, which couldn't be modified at all.
The M stands for modular. A first-class car can be transformed into a second-class car and vice versa.
The M might also stand for maintenance, made simpler and more accurate with the help of hundreds of sensors connected to artificial intelligence.
There are sensors all over the train.
From the initial sketches of the TGV-M to its first run on the French rail network,
320 kilometers per hour is almost 100 meters per second. There's no margin for error.
with a peek behind the scenes to see how they're built and tested, combined with 3D animation, we'll tell the story of this extraordinary 10-year industrial venture that created this train. The embodiment of the future of high-speed travel in France and abroad. Now arriving, the TGV-M. No fewer than 10 industrial sites are involved in the production of the TGV-M. It was in Saint-Ouen, in the outskirts of Paris, that the silhouette of the new train first saw the light of day. It might seem surprising, but this technological treasure was born from a few strokes of a pencil.
We integrate the technical requirements as soon as possible, which means that we have to come up with some very innovative solutions. But we always start with a research phase. That research can be done with nothing more than a pencil and a pile of Post-its. That's how it starts.
The speed at which these sketches are being created belies the complexity of the task. For this new train, the designers had to come up with a worthy successor to the TGV Duplex, which broke world records by surpassing 574 kilometers per hour. The list of requirements for the TGV-M is long and ambitious. It also marks a first in the history of French rail. An innovation partnership between the SNCF, the traditional rail company and sponsor, and manufacturer, Alstom.
The competition had to catch up to our TGVs. We also had to get a head start on facing new challenges, such as global warming.
We wanted to drastically reduce what we call the global cost, which is to say the cost of acquisition for our clients, but also maintenance costs over the next 30 years and energy costs.
Another goal was to make the product more attractive by giving it a higher passenger capacity than the old TGV trains, and by adding equipment on board that would improve the customer experience.
The SNCF, for their part, wanted a TGV that would cost less, consume less, have a higher capacity, and be more comfortable and adaptable. A seemingly impossible equation with multiple unknowns. But luckily, they could depend on France's experience with high-speed rail travel.
The idea was to draw on the heritage of BB locomotives, namely their characteristic design and the panoramic aspect that was also found on the first TGV trains.
Today's design is a nod to the locomotives that once pulled Capitol trains between Paris and Toulouse, but it's also a symbol of a technological breakthrough that came about with the first TGVs. In the mid-1970s, when the first high-speed train in France was designed, it was well ahead of its time. It had to reach the commercial speed of 270 kilometers per hour, which was about 100 kilometers faster than most trains at the time. In order to achieve that goal, they had to revolutionize the traditional rectangular shape of locomotives.
They realized how much the shape affected the aerodynamics of the train, as the speed gradually increased to the 320 kilometers per hour we have today. There are around 4 meters between the very tip of the nose and the first wheel truck. You can barely tell the difference between the locomotive and the cars. It's all one continuous line that starts at the tip of the nose and continues straight through to the very back of the train.
In addition to breaking speed records, this new train also had an original architectural design. The bogies, or wheel trucks, were not attached in the usual way. Instead of having 2 sets of wheels under each car, they were placed between the cars, resulting in a smaller total number of wheels.
Reducing the number of wheel trucks meant less drag, and having a fairly rigid connection between the cars prevented any sort of wave-like movement. That resulted in a high-speed train set that was very stable in terms of railway dynamics.
The vocabulary of that first design was a complete break with the other trains that were being built at the time. It was very innovative and became a reference in high-speed transport.
The subsequent generations all maintained the principle of articulated cars, but gradually introduced improvements to performance, cost, comfort, and environmental impact. After the first TGV was put into service in 1981 in the form of the famous bright orange TGV Southeast, the second generation switched to a blue color scheme.
In the 1990s, the introduction of a second generation of trains meant that high-speed trains could be found all over France, on the Atlantic coast, in the north, everywhere.
Many small adjustments were made for the TGV Atlantic, especially the one-level version whose upper part was reworked.
The TGV Atlantic was put into service in 1989 and went from 8 to 10 cars and 380 to 480 seats. Most importantly, the train, weighing over 400 tons, could travel at 300 kilometers per hour.
In the mid-1990s, a third generation of TGVs was introduced in the form of double-deckers. High-speed rail travel was so successful that certain lines were starting to be saturated, so they had to increase the capacity of the trains.
The TGV Duplex was the first high-speed train in the world to have 2 levels. It was capable of carrying 520 travelers per train at a speed of 320 kilometers per hour. A 4th generation of high-speed trains, designed exclusively by Alstom for the European market, has never circulated in France. The AGV, or Automatrice à grande vitesse, which can travel at more than 350 kilometers per hour.
Alstom used what it had learned when designing other high-speed products, such as the AGV, which is used in Italy, taking the aerodynamic profile of those trains into consideration when coming up with a design for this new TGV.
Even more aerodynamic than the AGV, this is what the locomotive of the TGV-M looks like. What are the improvements, and why is it shaped the way it is?
What you need to know is that 60% of drag, which is a force that opposes the motion of the train, comes from the locomotive. So it was essential that we come up with some innovations that lead the vehicle. Modern industrial tools, technological progress, and our ability to produce more complex pieces means that we're capable of doing things we couldn't do before, or at least not without resulting in unreasonable production costs. Today, we have computing power and software that makes it possible for us to work on areas we didn't know how to work on in the past.
More modifications have been made for the TGV-M than were made for the TGV duplex, with two goals in mind: to make it more efficient and to give it a distinctive look.
The shape of the nose is completely different. It's 1.5 meters longer than the old TGVs, which makes it more streamlined and enables it to pass through the air more easily.
We didn't want the shape to be boring. We wanted to give it character too, most notably on either side of the cabin, on what are known as the shoulders, which give the locomotive extra force and create an impression of controlled power.
On the central windshield, they removed the niches from the TGV duplex, so the windshield is now flat. One major element of the lower part was also redesigned.
The first wheel truck is a weak point in terms of aerodynamics, so we streamlined it. It's an important innovation compared to the old TGVs.
Streamlining the first wheel truck is important because it simultaneously improves airflow and decreases noise pollution.
The undercarriage may have been streamlined, but another particularly sensitive zone was completely transformed. The alcove reserved for the pantograph, the arm that extends out from the top of the train to make electrical contact.
The pantograph area on the TGVs was kind of a mess in terms of aerodynamics. There was a lot of equipment on the roof. So one of the innovations for the TGV-M was to remove as much equipment as possible from the roof and integrate those systems into the inside of the locomotive to get a simpler rooftop.
A lot of work was done on the pantograph to make it as streamlined as possible. Once again, minimizing and diminishing the turbulence around this important piece of technology was key.
The pantograph and the wheel truck were streamlined, and the aerodynamic profile was improved, but the locomotive has even more secrets in store. Some of them are paramount because they allow the TGV-M to carry more passengers than before. To discover what's hiding behind this new silhouette, we must travel to the factory where they're assembling an incredible technological puzzle, a massive, completely redesigned structure.
The biggest difference is that instead of starting with the old generation and making improvements left and right, we really redesigned it from the ground up. We asked what changes we should make to create something modern that reflects society today.
It's here in Belfort, in eastern France, that Alstom is producing this new age locomotive. On the same site where the first prototype of a high-speed French train, the historic TGV-001, was built in the 1970s. The first step in building the locomotive of the TGV-M here in Belfort was overseen by the R&D department after they received the designer's preliminary sketches.
Whenever we start a new project with the designers from Saint-Ouen, they present us with the sketches, and then we look at what's feasible or not. We went back and forth several times to figure out how we could make something that corresponded to what we wanted in terms of both design and aerodynamics.
That perfect balance of design and aerodynamics all begins with simple pieces of steel of all shapes and sizes, like this one here, that will make up one side of the locomotive.
The first step, which is sheet metal work, starts with unfinished pieces of sheet metal. There are a few parts that we buy pre-made, but mostly we just start with sheet metal that we cut out, fold, and then assemble into small subsections ourselves.
It takes more than 4,700 welding points to assemble this new locomotive, over 95% of which are done by hand. As the engine comes together, the small subsections become heavier and heavier, and more difficult to manipulate. When the large subsections are finally assembled, the skeleton of the locomotive is nearly complete. The metal must be heated up one more time, but not to be welded.
When you weld sheet metal, it causes a lot of deformation. It contracts, so we have to correct the sides to get them to be nice and even again.
Every measurement and every welding point must be checked before the locomotive is sent to the paint shop. 10 days later, the locomotive comes back out in immaculate shape. It's moved from station to station, where it's fitted out with the rest of its equipment in a very precise, choreographed dance.
The locomotive is kind of like a shoebox because it doesn't have a roof, but all the sides are closed. The rest of the equipment is put into place using bridge cranes. We're talking about blocks that are 3 meters long and weigh 3 tons that need to be put in exactly the right position. Once that's done, we can screw everything into place and connect the electrical wiring and plumbing. It will still have to be tested later, but that's really the step that makes the locomotive complete instead of just a steel structure.
Once it's fully equipped, this massive vehicle full of electronics weighs 50 tons. 10 tons more than an Airbus A320, and that's without the wheels. This locomotive is much higher tech than the previous generation, yet weighs nearly just as much to ensure good grip on the rails. The new locomotive is much smaller, however, even though it's more effective than ever. On the TGV duplex, all the functional blocks, including the transformer, were placed right in the middle of the locomotive. For this new design, they've been moved or reduced in size.
We redid the whole architecture of the locomotives in order to make them smaller. We changed how they're built. Instead of having 2 side corridors, there's just 1 central corridor, and the transformer is down below.
The transformer is used to reduce the voltage from the overhead lines from 25,000 volts down to 1,000 volts from the electrical equipment on board. Thanks to advances in technology, we've also been able to miniaturize the technical compartments. The third major innovation was to simplify the distribution of energy on board the train for systems that keep the passengers comfortable, such as their air conditioning. What was known as the common block on the old TGVs has been phased out, enabling us to reduce the size of the locomotive by 4 meters.
The fact that the new locomotive is 4 meters shorter than that of the TGV duplex results in an 8-meter reduction for the train overall. This changes the whole architecture of the French TGV, most notably with this new feature resembling a space capsule, which the designers of the TGV-M have baptized the graft. Why did they choose to use this medical term? What purpose does it serve? What makes it so revolutionary? To discover the secrets of this major innovation to the French high-speed train, we must travel to another Alstom factory, located 800 kilometers to the west, in Étré, near La Rochelle. To understand the primary purpose of the graft, we must take a look back at the previous generations of TGVs.
Right from the start, the basic idea behind the architecture of the TGVs was to have a locomotive on either side of a fixed train set in what was known as an articulated arrangement. The locomotives are independent vehicles. Each one has 2 wheel trucks. Each car shares a wheel truck, meaning that it stops in the middle of the wheel truck where the next one starts. The individual cars can't be connected on their own. If you want to add an extra car on the end, it has to be linked to the back of the locomotive.
In the designs for the TGV-M, one of the primary goals was to reduce production costs by standardizing the cars as much as possible for production in La Rochelle. Thanks to this graft, there's no longer any need to build a special car for the end of the train.
With the Euroduplex, we had 3 types of vehicles, which meant that there were 3 assembly lines. One for bar cars, one for the so-called intermediate cars, and one specifically for the cars at the end of the train. With the TGV-M, we have 2 production lines, one for bar cars, which is still different, and one for everything else. That's what we mean by standardization. At the end of the production cycle, we assemble the graft mechanically, which allows us to make the connection between the locomotive and
The graft has the same exterior shell as the regular cars and the same length of 3 meters. It serves the same purpose as the cars at the end did in the past, but with one additional advantage. It can carry the equipment that used to be located inside the locomotive or on the lower level of the bar car.
The graft is a new piece that we designed to store technical equipment. It contains all the energy storage equipment. The TGV-M is simpler than the older TGVs. They had 6 battery blocks, whereas the TGV-M has just 4, 2 per graft, to supply 110-volt power to the train.
But the benefits don't stop there, and its other features are even more surprising. In addition to the low-voltage batteries, the graft is also equipped to store energy in 700-volt batteries.
The energy storage feature is a new innovation for the TGV-M. Being able to store energy has several benefits, the first of which is keeping the passengers comfortable.
When there's an incident on the network that knocks out the power from the overhead lines, with our current TGVs, the air conditioning stops after 30 minutes. The lights dim, and the toilets are out of order. With the batteries, however, we can keep all those elements of passenger comfort running for 2 or 3 hours, which is long enough to deal with the technical problem.
Having batteries to store energy is good for more than just passenger comfort. Consider the hypothetical situation of losing power from the overhead lines once again. The TGV-M would be able to keep driving at a reduced speed of between 30 and 60 kilometers per hour.
The other advantage is that it can keep the train moving if the power from the overhead lines is knocked out during a storm, for example. The train can keep traveling for several kilometers.
That means the train might be able to reach a section of the rails with power or a garage where they could potentially transfer the passengers to another train. What's great about this graft is that it will allow us to clear the lines and resume regular traffic flow sooner after an incident on the network.
The last innovation enabled by the grafts on the TGV-M is that they make it possible to temporarily relieve stress on the national power grid by switching to energy from the batteries on board the train.
From time to time, we get alerts saying that the electrical consumption in France is higher than the means of production. Thanks to these batteries, we can reduce the amount of electricity the train is drawing from the power grid for an hour at a time. If we scale that up to 200 trains, it means eliminating an electrical consumption equivalent to that of a city of 50,000 people for 1 hour. That's a major innovation, and it's the first in the world.
Thanks to the graft, which is full of innovations, Alstom and the SNCF were able to come up with a standard car to be manufactured in the workshops near La Rochelle. With its brand new graft and mini locomotive, what will this new train look like? How did they manage to increase the space for passengers while simultaneously increasing passenger capacity? How has this train of the future been adapted for global warming?
The carbon footprint per passenger has significantly improved. It's 35 to 37% better than the old double-decker TGVs and 50% better than single-level TGVs.
The TGV cars take shape at the La Rochelle site. First, they create the shell of the vehicle, not out of steel like for the locomotive, but rather out of aluminium.
To make the shells of our train cars, we start with aluminum sections we receive from our suppliers. We take those aluminum sections and put them together. Then, to assemble them mechanically, we weld them. There are no rivets. Everything's welded.
The aluminium sheets are assembled primarily by robots, but a battalion of 80 welders work together to assemble the more complicated sections that would be too difficult or costly to weld robotically. Each shell has no less than 2.5 kilometers of welded joints. Once the welding is done, they must abrade certain sections to smooth out any swelling. And of course, another fundamental step consists in preparing the various pieces that will eventually contain the future equipment.
The aluminum sections we receive are unfinished. We cut the openings we need, such as windows, doors, and hatches, to access technical areas where the air conditioning and such will be stored. All of that's done on automated machining benches.
Once the shell is finished, the dimensions are analyzed using not a magnifying glass, but a laser.
It's not clockmaking, but every millimeter counts when we're making our structures.
Once the measurements have been verified, the structure is sent to the paint shop for 12 days before being returned to the production floor using a transporter. Then it's time for the last step, fitting.
Fitting consists of equipping each vehicle in the train set with all the necessary amenities for both its basic functions and elements of passenger comfort, such as seats, windows, floors, and carpets. Everything the passengers see is put in place during the fitting stage. There are some 5,000 items on a single train, so you can imagine the number of different things that go into every one of these vehicles.
During this final stage, one particularly strategic step is to finish all the wiring.
There are a lot of wires in a vehicle because the train is connected. There's approximately 1 kilometer of cables per linear meter of train. So for a vehicle that's 17 meters long, we have 17 kilometers of wire.
For the new TGVs, the Étré site took the opportunity to review the production process. New tools were created to make it more rational and ergonomic, such as this wiring arm.
By the time the vehicle reaches the fitting stage, it's all been assembled. So we can't go in through the roof anymore, only through the ends. So we designed a telescopic arm that we can use to put the bundles into place, which are the length of the vehicle, reducing the time it takes to hook up all the wires.
The train cars may be made in La Rochelle, but their interior design comes from the Saint-Ouen site. The teams from Alstom have a precious tool at their disposal to confirm that design. A panoramic screen that allows them to envision the interior of the train before it's industrially produced.
We have a screen almost 3 meters tall and 6 meters long. It lets us see some very precise details, such as the space between the trains, the ends of the cars, and the doors. It shows the interior of the train to scale.
In immersive mode, the novelty of the new design becomes apparent.
One thing you barely notice because of the black stripe is the relative smallness of the window frames. The windows are slightly less tall to get more horizontal visibility.
The interior of the train was designed to be much more comfortable than before, starting with the seats. They're much more rounded, and the headrests can be adapted to different body shapes. In addition, each seat comes equipped with certain features that are indispensable today, such as an outlet. The train will also have an excellent Wi-Fi connection that's up to 5G standards. Finally, the train will be quieter and let in more natural light, because the TGV-M has 25% more windows than the previous TGV. We enlarged the windows in the passenger cars and added windows to the sections between cars on the upper level. We even added windows in the bathrooms, but obviously, these are one-way glass.
Not only are there more windows than before, but they were designed with global warming and increased sunshine in mind. They're more efficient, as is the air conditioning system, which helps reduce the energy consumption of the train.
We use new materials that provide better insulation, such as heat-resistant films that are applied to the windows so that the sunlight doesn't warm up the inside of the train car. Finally, the major change was to the air conditioning system. It adapts to the number of passengers in the car. If there are no passengers in the car, the cooling system will detect that and reduce its energy consumption as much as possible.
There have been numerous changes for passengers, but also for the train operators themselves. The letter M in its name is synonymous with a major transformation.
The M in TGV-M stands for modular. What that means is that a first-class car can be transformed into a second-class car and vice versa, relatively quickly, to adapt to seasonal variations in traffic. Much of the interior equipment can be replaced extremely fast. It's fairly easy to add more luggage racks or space to transport bicycles, for example. We can also remove luggage racks and storage space to make more room for passenger seating and such.
Thanks to a system of interior rails, each car can now be transformed as if it were made of Lego. But the modular aspect also applies to the train as a whole. The architecture of the train can be modified, whereas TGV duplexes always have the same 8 cars.
The TGV duplex is always the same. It's not modular at all, so that's really an innovation for the TGV-M, that idea of preserving the advantages of an articulated train set, but also introducing the idea of modularity, which means we can remove 1 or 2 cars so we can have the TGV-Ms with 7, 8, or 9 cars.
These changes were made possible by the size of the locomotive. The new design is just 18 meters long instead of 22, for a total saving of 8 meters for 2 locomotives. The reduced technical space of the cars also saved 1 meter per car, leaving enough space to add a 9th. Since the graft now carries equipment that used to be transported on the bar car, or passenger cars, those cars can now be removed without losing any important features. For the SNCF, this new TGV offers both greater flexibility and a higher passenger capacity.
The INWI version of the TGV-M will be able to carry up to 600 passengers, compared to just 509 or 550 passengers on the 2-level TGVs we have today. The WIGO version will be able to transport up to 740 passengers, as opposed to just 630 today. That means that the 2 trains hooked up to one another could accommodate nearly 1,500 passengers at a time.
But there's still a lot of work to be done before these trains can start carrying passengers. There are numerous stages to the process, such as when the first locomotives manufactured in Belfort arrive in La Rochelle, so they can put together the first TGV-M train set.
The first time we put a whole train set together is always very symbolic, because it's the result of years of design work. It's the moment when the new train is born, and it marks the start of the testing phase, so it's really the beginning of the story.
A story in which the TGV-M will have to show what it's made of. To what kinds of trials will this new train be subjected? How will it be ramped up before the commercial launch? And why does the test phase take so long?
Roman for Dominique.
The time from putting together the first train set to the end of the project, when the train is approved for transport on the French rail network, is usually around 12 to 18 months. Our goal is to be able to do it in 12 months, which is a really big challenge.
The massive Alstom site near La Rochelle features a rather particular service where almost an entire train can be tested without actually having that train on hand. It's known as the Train Lab.
For the TGV-M, we invested a lot in the train lab so we could test out all of its features beforehand. By features, we mean the passenger entrance where the passenger pushes a button to open the door and things like that. That's what we reproduce in the train lab for various physical elements, such as doors, wiring, windows, and computers, but also digital elements, such as models of the motor and other parts. It's a way for us to validate features and save time on development in order to get a train certified before it's actually been built.
It's like having a rough draft of the train before the first train set is actually completed. You can see it driving virtually here to test the passenger information display systems. This new tool, which has been used throughout the development and testing of the TGV-M, has already become very important.
For previous projects, between the moment when we assembled the first train set and the moment when we turned it on for the first time, it took 3 to 4 months. For this train, it took us 2 days. It saved us 3 or 4 months of checking for problems and searching every single wire of the 200 kilometers of wires inside this train. We saved very valuable time.
The Alstom teams have been developing this incredible tool since 2009. The first test bench was fairly limited in terms of capacity, but the modelling available today means that they can simulate, for example, all of the wiring in the entire train. Year after year, more and more digital features are being added.
Much of the train is digitized today, but we have to keep going until as much of it is digitized as possible, because it will save all of us time, both during the development and also once the train is up and running and ready to get certified and do trials on the rail network. We hope that as we continue testing this train and it keeps growing in maturity, this tool will remain helpful, because we won't have to do all our testing on the train itself. It will also optimize costs for us, because we won't have to use actual trains. We'd rather use our trains to carry passengers than for testing.
Despite the extensive digitization of the TGV-M, some physical testing is still required. One of the first tests takes place on the same site in Étré in what's called an environmental chamber. Sensors have been placed inside the cabin of the locomotive. Using heat lamps, it will be subjected to temperatures worthy of the Sahara Desert to test the cooling system's response.
We have sensors that measure the temperature and humidity levels to make sure the air conditioning is responding correctly to the extreme conditions to which we're subjecting the cabin. It's the same for the technical compartment, where we put sensors to measure the temperature, airflow, and humidity levels to ensure the air is circulating well enough to keep the engine block and electronics cool. That's the first thing we check. If there's a problem there, the train won't be able to travel at the speeds at which it's meant to travel.
The TGV-M hasn't been put into circulation yet, but it's already traveling across Europe. One of its destinations is Vienna, the capital of Austria. In another environmental chamber there, the French train will be pushed to its limits by recreating some even more extreme conditions.
A miniature section of the train set has been sent to Vienna to be tested in the environmental chamber of the Vienna Arsenal, which is unique in Europe. The trials we're doing there will be used to confirm and approve the climate control on board the train, but also another element that we can't test in Étré, which is the speed of the train. They can subject it to wind, snow, sun, and all sorts of other things there.
In Vienna, they can simulate wind speeds of up to 160 kilometers per hour to test the heating and insulation of the train cars, with some rather unusual passengers on board.
We simulate the presence of passengers by putting hot water bottles inside the cars. Those bottles are a certain temperature, which is the normal body temperature of humans, and they're placed beneath the seats to reproduce the energy put out by each passenger.
Once again, like with the anti-UV film placed on the windows, the designers of the TGV-M have taken climate change into account in their plans.
We measure the temperature and humidity in different parts of the car to see if the air is flowing as we expected, which is very important. If it's very hot at one end of the car and very cold at the other, that's no good, because everyone will be unhappy. So the car has to be prepared to go from minus 25 degrees Celsius with snow and frost, which are very detrimental to railways, to very hot temperatures. We subject the train to extreme temperatures in testing, because unfortunately, we know it can easily get up to 40 or 45 degrees in certain areas nowadays.
The trials in Étré and Vienna are mere warm-ups for this athlete that will one day have to travel Europe at 320 kilometers per hour. It will have to accelerate much more quickly than is possible in La Rochelle or Belfort. The train's first high-speed travel will take place not in France, but abroad in the Czech Republic. To be exact, on a site unlike any other in Europe, located 40 kilometers east of Prague, Velím.
Velím is a circuit where we can test the overall functioning of the train at speeds of up to 200 kilometers per hour. Velím is essential in getting the authorizations we need to put these trains into service on our network.
A legacy of the communist era, this site has two tracks, one nearly 4 kilometers long and another more than 13 kilometers long. It's the only circuit in Europe where trains can be tested at speeds of 200 kilometers per hour. This is essential because at this stage of its development, the TGV-M cannot run on the regular network without risk of disturbing commercial traffic. The only solution would be for it to run at times of day when the current TGVs are not on the tracks.
Basically, we would have to take a given line and shut it down, then run the train at night to try to make sure it's compatible. Today, we wouldn't have enough time to do that, and it would be very expensive to do it on the network.
The trains they use for the trials obviously don't look like normal trains. They're not equipped with seats or passengers. Instead, the travelers it will carry one day are represented by weights scattered all along the length of the train. Using wiring and monitors galore, the TGV-M will be examined from every angle, in hopes of finding a problem as strange as that might sound.
We cannot drive a train at 320 kilometers per hour without first making sure it's safe at 150, 160, or 200 kilometers per hour. We start out very simply at 100 kilometers per hour to check the train's overall behavior. Then we ramp it up to 200 kilometers per hour and examine how the train responds in terms of electricity, stability, and any potential traffic safety issues. Velim is useful for that too, to highlight any areas that might be problematic, so that we can resolve any issues early on and avoid trouble once the train is in commercial service.
Alone on its circuit, the TGV-M will go around and around, travelling 15,000 kilometres over 6 months at all times of the day and in every kind of weather.
The test train will run 5 days of the week, day and night. In Velim, it gets down to -10 or -15 at night, and it snows. So we'll also be able to check how the train responds to snow in order to make sure the brakes function properly no matter the conditions. We'll put black soap on the tracks too, and then try braking on that specific section to reproduce the problem of wet leaves accumulating on the tracks in the fall.
By its second day at Velim, the test train has already been able to run at 200 kilometers per hour for 350 kilometers. None of the older generations of TGV trains reached this stage so early in their testing. Once all of the objectives have been met during these 6 months of testing, it'll be time for another important step in the TGV-M's history: driving at 320 kilometers per hour on the French rail network.
French people are used to traveling at 320 kilometers per hour, but it's really quite something. It's almost 100 meters per second. There's no margin for error.
Before attempting to hit 320 kilometers per hour, the TGV-M took its first steps in France on a section of tracks that were closed to traffic. It was an emotional moment for everyone.
Naturally, after so many months of preparation, when you see the trains start to move along the national rail network for the first time, it gives you goosebumps. It's a pretty incredible sight.
Inside its cabin, which was redesigned with the help of drivers, the TGV-M has begun to travel across France from west to east. Strangely, as you watch the tracks go by, the feeling of speed is less impressive than in the older TGVs.
I wouldn't call it trivial because you still hear some of the same noises you used to, but it's much quieter and it's comfortable. It's like going from a classic car to something more luxurious. You don't have the same feeling of speed. That's what it's like traveling on the TGV-M.
Hidden away from prying eyes in the Alstom hangar in Belfort, the TGV-M is preparing to finally break the symbolic barrier of 320 kilometers per hour. Each new phase in testing starts with a briefing.
Latest update, I asked permission to boost the train.
The teams have scheduled every bit of testing down to the last second, but things always come up at the last minute. The last few days have had their fair share of surprises on the site chosen for these crucial tests. The Rhine-Rhône high-speed line between Belfort and Besançon.
All sorts of unexpected things can happen. A measurement chain can break and stop us in our tracks. The windshield wipers could stop working in the middle of a downpour. A truck could catch fire beneath the lifting platform the night before, preventing us from reaching the speeds we had been targeting. That's what testing is all about, dealing with a constant stream of problems.
The ability to improvise is all the more important as these trials are taking place amidst commercial traffic. Regular passengers will be travelling on the same tracks within minutes of the TGV-M.
This step is very important for our tests, of course, but we're working around commercial traffic. When something starts to go wrong, it can get in the way of commercial traffic, but it also throws off our own schedule. It puts more pressure on the team, and as soon as something comes up, we have to face it head on and talk to the right person right away to make sure it's handled quickly.
That day, after finding the source of a new technical issue and repairing it in record time, the testing team was finally able to drive the train at full speed, reaching and even surpassing the crucial target of 320 kilometers per hour.
Hitting 320 is a big turning point in the project because it's the speed at which the train will be traveling most of the time. The stakes are high because it will determine whether we will pass all the tests in order to put the train on the market.
320 kilometers might be crucial, but it's still just one step in the process, as the train must actually be able to go well beyond this nominal speed.
Some tests call for us to go at 320 plus 10%. The train will drive at more than 350 kilometers per hour to ensure that once it's in service, it has enough margin for error to be able to carry passengers safely.
The new TGV is technically capable of traveling even faster than 350 kilometers per hour. But that argument is primarily for export, because in France and the cross-border areas, its maximum speed will be limited to 320 kilometers per hour.
We could travel at 350 or 360 kilometers per hour, but it would only save us a few minutes. However, the increased costs in terms of wear on the infrastructure and the trains themselves would throw off the whole economic model. In Europe, the overall trend isn't towards faster travel, but rather improving the energy impact and carbon footprint of high-speed trains.
Given the climate change challenges and the current energy crisis, the TGV-M holds a lot of appeal for the international market. It also has another major economic benefit that gives it an edge over the competition, a drastic reduction in maintenance costs, largely due to predictive maintenance.
Our goal is to be able to anticipate problems. Predictive maintenance is a major innovation compared to our old TGVs.
The SNCF's first maintenance center to be adapted for this new model is located outside Paris. It's known as the Southeast European Technicenter.
The Technicenter is where we handle fairly short maintenance operations that last from a few hours up to a week. There are 4 Technicenters for TGVs in Paris. The Southeast European Technicenter, where we are now, is the pioneer. It was the first Technicenter to work on TGVs in 1981. So history is kind of repeating itself, because once again, it will be the first Technicenter to welcome the new TGV-M.
The warehouse is still undergoing transformation as it welcomes one of the TGV-M test trains for the first time. The renovations of the Technicenter will take 5 years and cost a total of 280 million euros.
Nothing had been invested in it for 40 years. So first we needed to do some general renovations and adapt it for the more ergonomic working conditions of today. But of course, we're also making some specific changes just for the TGV-M.
These changes are necessary because of certain modifications to the structure of the train, such as the addition of the graft and the new location of the transformer.
On the roof, the bridge is now 4 meters high instead of 3.5 in order to leave more space for the windows. On the TGV-M, the windows are put in place from the outside, which is more practical than installing them from the inside.
They also had to create an opening on that bridge with a sliding platform in case they needed to work on the new part known as the graft. And that's not all.
The transformers will now be put in place from the bottom rather than the top. So we're going to build a jack that's usually used to put all the axle trees in place on our TGVs.
On the most heavily trafficked TGV line, in addition to the Southeast European Technicenter, the Lyon-Gerland Technicenter and the maintenance stations in Marseille and Nice will also be affected by this initial phase of renovations. Over time, all Technicenters connected to a Parisian station will be transformed, but the SNCF hopes that the TGV-Ms will spend much less time being repaired than the TGV duplexes.
Our goal is to reduce maintenance costs by 30% compared to one of our current TGV trains over the course of the TGV-M's lifetime, which we estimate at 30 years.
Until now, pieces of the TGV would be replaced either after breaking down or becoming faulty, or at regular intervals to head off potential problems, which is called preventive maintenance. This has a considerable impact because it means immobilizing a train that didn't necessarily need to be taken out of commission, or replacing parts that could have been left in place for longer.
The maintenance of the TGV-M is a complete break with what we've done in the past. What we do these days is very repetitive and systematic. In the future, we'll do maintenance as needed.
The TGV-M marks the beginning of a new era for the SNCF, moving from preventive to predictive maintenance. They no longer have a set lifetime for a given piece of equipment. Instead, there are sensors that monitor each part.
There are sensors all over the train, on the air conditioning system, in the air compressors, and in the bathrooms, even the passenger seats. We're monitoring every single part of the train.
Several hundred parts are hooked up to sensors that are constantly taking measurements and sending data. Part of that data is stored inside the train, while the rest is analyzed directly by an artificial intelligence that handles up to 500 variables and can issue alerts to the conductor in real time.
For example, we have real-time monitoring of the temperature in the cars and of any issues with the bathrooms, plus a number of services that are essential for our clients.
Some data can easily be interpreted on board, but the more complex functions of many other pieces of equipment must be compared to other TGV-Ms in circulation. That's why 25,000 variables are transmitted to a central computer every 100 milliseconds.
This data is sent to communication modules that pass through antennas on the roof and use 4G, then 5G to send some of the data back to the servers on the ground.
On the ground, in their maintenance centers, another artificial intelligence will interpret all of the data collected from the entire fleet of TGV-Ms. This way, it'll be able to detect any problems in their early stages, predict if a part is reaching end of life before it breaks down, and enable teams to intervene in advance.
Predictive maintenance will be used to cut maintenance costs. The other benefit is that it will allow us to have more TGVs in circulation at any given moment in time, because we'll be able to anticipate any problem. So we'll have fewer unexpected incidences in the network.